we say that the random variable is uniformly distributed over an interval AB if its PDF is constant over that interval. So now this is the notation for a uniform random variable x over the interval AB. X is said to be a uniform random variable with two parameters a and b, which are the endpoints of the interval over which the uniform random variable is defined. Now, PDF of a uniform random variable x with parameters a, b is of the form 1 by b minus a for x greater than equal to a, less than equal to b, and 0 otherwise. And we know a continuous random variable takes on values where its PDF is non-zero. So in this case, the uniform random variable takes on values a to b. Now, if we plot the PDF of a uniform random variable, so we know for x greater than equal to a, less than equal to b, the PDF is 1 by b minus a, and otherwise it is 0. So in this case, for a uniform random variable, now for this first, let's recall that area under PDF gives us probability. And in this case, area under PDF is simply area of rectangle. So if you want to find probability involving a uniform random variable, we can either integrate the PDF over that interval, or we can just see from the graph of the PDF. As we know, area under PDF is probability, and area under a PDF of a uniform random variable is simply area of a rectangle, which is easy to find. So for instance, say x is uniformly distributed from 1 to 3. If we want to find the probability that x lies between 2 and 3, we can either integrate the PDF from 2 to 3, or we can just simply see from the graph area under PDF, right? As area under PDF is just area of rectangle, which is easy to find. We know this is the PDF of the uniform random variable. The probability it lies between 2 and 3 is the area of this rectangle, which has a length 3 minus 2, 1, and it's so basically we have this rectangle where this length is 3 minus 2, 1, and this width is 1 by 2. So in this case, the area, so we can just simply find the probability that x lies between 2 and 3 as just the area under the PDF. Because the area under the PDF is just this rectangle with area 1 times 1 by 2. Now, CDF of a uniform random variable x is of this form, and we can get this through, we can derive this by integrating its PDF. So to find any probability involving a uniform random variable, just like for any other continuous random variable except normal, we can either use PDF or we can use CDF. When we use PDF for uniform random variable, we actually have two options. We can either integrate the PDF, just like we do for other continuous random variables, or in this case, we can just simply use the graph of our PDF, as area under PDF is area of rectangle, right? So in this case, we have this option. Like for any other continuous random variables, you can find the probability using PDF or using the derived expression of the CDF. In the case of PDF, you have two options. Just like for the continuous random variables, we can integrate the PDF, or we can just simply use the graph of the PDF. As area under PDF is just area of rectangle, which is easy to find. Now, this is the expected value and variance of a uniform random variable x with two parameters a and b. Expected value is just the average of the two parameters, and this is the variance, and this we can derive using its PDF. Lastly, for uniform random variable, there's an important property that if we have x, the uniform random variable, with parameters a and b, the probability that the random variable x lies inside a subinterval of a depends upon the length of the interval and not where the interval is located. What this means is, say we have x, which is uniformly distributed from 1 to 5. Then without doing any calculations, we know the probability that the x lies inside any subinterval of 1, 5 of length 2 is the same, right? So these are all subintervals of the interval 1, 5, which has length 2. So the probability it lies inside any of these subintervals which have the same length, in this case 2, is the same. Similarly, the probability it lies inside any subinterval of 1, 5 of the same length of length 1 will also be the same. So the idea is that for a uniform random variable that has two parameters a and b, the probability it lies inside any subinterval of ab is going to be the same for those intervals that have the same length. Right? So if x is a uniform random variable with two parameters a and b, so the probability of lying inside any subinterval of ab depends upon the length of the interval. Those subintervals of ab that have the same length, they will have the same probability that x lies inside them. Like over here, the probability x lies inside a subinterval of 1, 5 of length 2 is the same. The probability x lies inside a subinterval of 1, 5 of length 1 is the same. So the probability that a uniform random variable lies inside any subinterval of AB depends upon the length of the interval and not on where the interval is.